There are two types, I told you. One is forced convection. One is forced convection, and the other one is natural convection. Natural is also called as free convection. So this forced convection is of two types. It is internal flow forced convection, and the other one is external flow forced convection. Okay, in this we have completed the internal flow forced convection. Now we are starting this one, the external flow forced convection we are looking at. Okay, so it is external flow forced convection. Okay, so in external flow forced convection, the flow will be over a body, a liquid. Better to say fluid. It need not be liquid, it can be gas also. So I'll say fluid. Over a body, a fluid will flow over. Okay. The body can be anything. The body can be a flat plate. The body can be a cylinder. The body can be a sphere, or it can be a bank of tubes, or it can be a non-circular tube. It can be anything, but over that body the fluid will be flowing over. Let me take a uh, cylindrical cross section here, and air is flowing over it. Okay, so this will be the case for forced convection, and this forced convection is a flow over a body. Okay, and you can take the example of a flat plate. This is a flat plate here, and air is flowing over like this. Okay, this is the airflow. Then this is a body. This is a flowing over. So these are all the cases for external flow forced convection. So external flow forced convection will be a flow over a body. Flow over a body. This one. Okay. So if you refer to your data book, move to the index, the contents page. Then in this, you move to convection. In convection, you look at two types of convection. One is forced, the other one is free convection. In forced convection, we have two things here. The first one is the external flow, which we will be studying now. Okay, this one we will be studying now. The internal flow is already completed. So let's move to page number 121. Okay, I have made it as a separate PDF here. So you can look at it's page number 121. Here the properties are to be evaluated at something called as a film temperature. Okay, previously we were taking the properties of a material at bulk mean temperature in internal flow, whereas in external flow we will be calculating the properties at something called as a film temperature. This is very important thing here. Let me write it down for you here. Here the properties are evaluated are evaluated at film temperature. Film temperature. The film temperature means what? TF is equal to T plus T infinity by 2. Here, T is the temperature of a solid and T infinity is temperature of fluid. Okay, here in data book you can see it. It is T wall he has written, TW he has written here. Okay, TW means according to him it is a plate surface temperature. Okay, he has written plate surface temperature because he is dealing with a flat plate initially. Okay, initially he has written the formulas for a flat plate here. Then you will have for the cylinder, you will have for sphere and all. Okay, if you keep moving your pages, you will see all that. This is all for the flat plate. Here you can see flow or cylinder. Okay, and if you further move on, you can see flow or sphere, non-circular sections also you can see flow or spheres, you can see like a flow or tube tanks, you can see. Again, these are all the various cases that I've already written there. So all those things can be there. But here we're essentially discussing what is the temperature that we are going to consider for evaluating the properties of the fluid here. Okay, so you have to evaluate them at a film temperature, wherein in film temperature you will have two things, that is temperature of the fluid and the temperature of the solid. This is a fluid and this is solid. Okay, simply put, it is a average temperature of solid and fluid. Okay. So that's how you can remember this. So it is T wall plus T infinity by 2. Right. So that's the film temperature story. Okay. Next thing is, once you find out the film temperature, what is the next thing you do in internal flow? You actually get what is a kind of a flow here, whether it is a laminar flow or turbulent flow you will do in internal flow. Even in the external flow, the same thing you will follow. Okay, so laminar or turbulent. How do you say it? How do you say it? Somebody respond.
Reynolds.
Somebody please respond. You will use the Reynolds number. What is the Reynolds number value? The critical Reynolds number we call it. Okay, if it is above this, RE is greater than REC, that implies it is a turbulent flow. If RE is less than REC, it will be a laminar flow. In any kind of flow you can take. So what is the critical Reynolds number value here? Yes,
2300.
somebody please respond. 2300. And this 2300 is not correct. Okay, this 2300 is in a case of internal flow. You refer and look at this part here. Under laminar flow, he has written what is the RE value. Okay, and under turbulent flow, also he'll be writing what should be the RE value. This is yeah, yeah. Here you can see the turbulent flow. The RE value should be greater than 5 into 10 to the power of 5. Okay, so for a flat plate in the external flow, REC value is 5 lakhs. 5 lakhs. That is 5 into 10 to the power of 5 for flat plate. For flat plate. Okay, and you got this value from page number 121. Is it right? Yeah, page number 121, you will have this value. Okay, you need not remember this. Okay, it's good to remember, but even if you forget also, you can refer to your data book and get this value very easily if you refer to the appropriate page number. Okay, and if this is REC, you are writing it for a cylinder. If you are writing it for a cylinder, what is the value? If you are writing this REC for sphere, what is the value? Also, you should be writing it. So, can you please refer to your own data book and tell me what is the value for the cylinder also? Okay, this is the flow over the cylinder case. Where did he write this? See here, for each case, is giving you the Reynolds number values. Okay, here also the Reynolds number values are mentioned to you. Okay, based on the Reynolds number value that you are getting, you will actually choose the kind of Nusselt number formula like in your internal flow, and same thing you will follow here for the cylinders, like the values are given to you here. The range of RE is given everywhere for every problem. So based on the range of RE, you will actually choose the kind of formula that you're going to choose here. Okay, so even this is the case for spheres also. You can have a look at all these things. This has been a problem of RE. You can see a range of RE, range of RE, range of RE. Likewise, you can keep seeing for all the cases in a given problem. Okay, but most of the times the case will be of a flat plate. So I'll give more concentration to the flat plate case in our explanation. So remember this 5 into 10 to the power of 5 clearly, and so you write these values for yourself. Let's move on. Once you have these things in your hand, you can go and solve the problem directly. Let me go to the problem. Anything that is remaining, I'll be explaining it using the problem itself. So follow carefully. So here there is a process that is happening and water is there in this. So you have to write what is the material here. It is water flows over a plate. Okay, it is a flow or a plate. So you have to write that it is an external flow problem, external flow over flat plate, external flow over flat plate. So that is the second thing that you have to do. And let's write what is given in the question. The flat plate is maintained at 10 degrees centigrade is given in question. So temperature of the wall is 10 degrees centigrade and free stream velocity is given. Velocity means V or u infinity also sometimes it is shown. Anyways, it is 0.3 meters per second, and he's asking you to find out, determine the hydrodynamic boundary layer thickness. Okay, hydrodynamic boundary layer thickness is first one. Boundary layer thickness, and thermal boundary layer thickness. Thermal boundary layer thickness, and local value of friction coefficient. Local friction coefficient, and average friction coefficient, heat transfer coefficient, H. What is the H value is asking you? What else is asking? Heat transfer coefficient, and the refrigeration necessary to maintain the plate at the given temperature. Means, what is the meaning of this refrigeration means? Kind of the cooling you have to update. So simply is asking Q is equal to H into A into delta T. What is this? He is asking. That is a refrigeration meaning. Also find the values of displacement and momentum thickness. Displacement thickness. Displacement thickness and momentum thickness. See, all these terms you must have learned in your fluid mechanics itself. Okay, while learning the course of fluid mechanics, you must have learned all these things. Okay, so if you don't remember what they are, kindly go refer uh, fluid mechanics textbook. You will get that. Okay, right here we can see what is called as a hydrodynamic boundary layer. Delta Hx is a hydrodynamic boundary layer thickness. Okay, so this is delta Hx. He's asking you to find. Next, what is the thing he's asking you to find? Delta Tx. Delta Tx means thermal boundary layer. Okay. Next one is local friction coefficient. Local friction coefficient means CFX. Next one is average friction coefficient. It is CFL bar. What is the value he's asking? Okay, anyways, H and Q he is asking. Also he's asking what is the displacement thickness. Displacement thickness, you can see here, it is simply delta X. Also, you have momentum thickness, it is delta IX. These are the things. And what are the formulas for finding all this delta Hx? Here you have the formulas. Okay, all the formulas for finding, even this one also. Okay, if you can find all these six things, almost you are done in this particular problem. See, for finding this, what you have to do is you will have to actually find out the Reynolds number first. And by Reynolds number, you're done with hydrodynamic boundary layer. Okay, based on hydrodynamic boundary layer, you will find the thermal boundary layer. Based on hydrodynamic, you will find the thermal boundary layer. For that, you need Prandtl number. Okay. Next, if you know the hydrodynamic boundary layer, you can find out the displacement thickness and momentum thickness also. So first thing to do here is to find out the Reynolds number value. Once you find out the Reynolds number value, you can find out the hydrodynamic boundary layer, and not only that, you can find out the friction coefficient also, the local friction coefficient with Reynolds number and average friction coefficient with Reynolds number you can find. Okay, so in the question he has given the size of the plate is 1 meter by 1 meter size is also given in question. So what you have to do here? Okay, you have to find out the Reynolds number. So before you find out the Reynolds number, what you have to do? You have to calculate what is a film temperature. This is the first thing you should do. Okay, here on the top have something called as film temperature that you must find out first. Film temperature is T wall plus T infinity by 2. So T wall is given in question. T wall is given in question as 10 degrees centigrade. T infinity is 30 degrees centigrade. T infinity is 30 degrees centigrade given in question. So let me write this T infinity here. It is given in a question itself. So this will be equal to 10 plus 30 by 2. So what is T film? It is 20 degrees centigrade. Okay, so what I have to do? I have to get values at properties at 20 degrees centigrade for water. So in your data book, go to the water page. Okay, where you will have this water? You will have it in page number 30. Page number 30, you will have liquids. Starting from 30, you will have water there. This is a water. Yeah, here we go. So since it is 20 directly in the question, you need not do any interpolation here. You will get the property values bit easily here. So let's keep it aside, and you will keep these properties at the top right corner of your page. I already told you. So leave a place there, and then move to the calculation of a Reynolds number. What is the Reynolds number value here? The Reynolds number formula you have to know. Tell me what is the Reynolds number formula, somebody?
Rho VD by mu.
Rho VD by mu. Okay. So this is also can be written as VD by mu. I have not written D intentionally here. Okay. In place of D, we will have something called as L, or you can have X also. Okay. If he is writing REL, meaning the complete length of the uh, plate has to be taken. If he is writing L, total length of plate has to be taken according to the question. Let us say he is writing RE. Let us say REX if he is writing. Okay. What is the meaning of this X? The meaning of this X is till the X value. That is, you are calculating the Reynolds number over entire length in the first case. Okay, over entire length in the first case, and in the second case over the given X length. Okay, this length need not be the complete length, that is the entire length. It can be something less than the actual length. So here you will not be using a diameter. You will be using a diameter. Diameter is a critical dimension in case of an internal flow. Here, in case of an external flow, in external flow, length is the critical dimension. See, don't confuse the word length here. When I mean length here, it is the direction along which flow is flowing. Flow is flowing. Okay, let me give you an example. You will understand this better. Okay, let me say this is a flat plate. Okay, this is a flat plate, and its length is 5 centimeters here and 3 centimeters here. Okay, and fluid is flowing like this. This is a fluid flow direction. Okay, this is one case. And let me draw the other case also. Okay, it is also similar case. 5 centimeters and 3 centimeters. And here the fluid flow is in this direction. Okay, so if this is the case, what you will do in this problem, you have to take the x is equal to 5 centimeters. Why? You have to take the dimension along which the flow is happening. This is the dimension along which the flow is happening. So the parallel dimension to the flow will be taken simply. So it is 5 centimeters in this case. Here in this case, what is the parallel dimension to the flow? It is 3 centimeters. So x or L should be taken with respect to the dimension that is parallel to the flow. Sorry, this should not be 5 centimeters here. I should write 3 centimeters here. Right? Is it clear to you all? You have any doubts at this level? Please ask it. Okay, I'm trying to give you an overview of how to use the things that are there, the kind of nomenclature that is there in the data book actually. See, you will be finding the various things here. Let me erase this completely, then you'll be understanding it a bit better. So whatever. So you can see here. See, in the superscript, sorry, in the subscript is mentioning the x values, is mentioned in the L values. Even for RE, he will mention REX is giving you, REL is giving you. Okay, so there is a difference between your REX and REL. So REX means what? Reynolds number from the starting till the distance x. Okay, leading edge means the starting edge, and Reynolds number at location L. That is means for the entire length you have to take if REL has to be taken. Okay, so that's how we should go about the calculation of RE. Anyways, let's come to our problem to calculate REX now. It is VD by, sorry, it is VL or X by nu, that is equal to V is given in question to us. What is the value given to us in the question? Somebody tell me. 0.3 meters per second is given in question. From the question, tell me what is the x value?
1.
1. Okay, either it is flowing in this direction or in the other direction, it doesn't matter because both are the same direction. You will get the same. What is new? It is not known. You have to get it from the data book. So move to your data book. In data book, move to the page number 30. You will find the properties of the water, and at 20 degrees centigrade you need the new value, that is a kinematic viscosity value. It is 1.006 into 10 to the power of minus 6 meters square per second. Page number 30. So new value is 1.006 into 10 to the power of minus 6 meters square per second. That is the new value. substitute all of them and get it. The 0.3 into 1 by 1.006 into 10 to the power of minus 6. Tell me this value. What is the value of the Reynolds number?
298,210.7
298 210 0.73. Okay. So you can observe that the Reynolds number value is less than 5 lakhs, isn't it? It is only 2,98,210. So it will be less than 5 lakh. So REX is less than 5 lakh. That implies the flow is laminar. Flow is laminar. What is the use of this laminar? Once you are sure that the flow is laminar, you can refer to all the formulas that are given under the laminar flow section in the data book. So if the flow is laminar flow, you can use all the formulas that are given to you here under this laminar flow. So let me write all those formulas here. Right. You need delta Hx, which is equal to 5 into x into Rex whole to the power of minus 0.5. Also, you need delta Tx, which is equal to delta Hx into Prandtl power minus 0.333, and delta x is equal to delta Hx by 3. I'm simply writing whatever the formulas that are there in the data book. Delta Ix is equal to delta Hx by 7. Next, what is the thing? CFX here also you need. The CFX, this is a local friction coefficient, 0.664 into Re power 0.5 minus 0.5, and CFL bar, the average one, is 1.328 into REL here, or minus 0.5. So here you will have to substitute the appropriate values here. So you have to substitute it here. It is 5 into the x value is 1, and the REX value you have found out some 2,98,201.73 whole to the power of minus 0.5. Tell me what is the value of delta Hx now.
2730.43.
Yeah, kindly repeat it again. 2730.43.
2730.43.
Did you put this minus in your calculation?
0.009.
9.15 into 10 to the power
9.
minus.
Hmm. Most of the students will miss this minus and do a mistake here. This minus should be there. Okay, if that is missing, the whole thing is going to be a wrong value. It is 9.156 into 10 to the power of minus 3 meters. Okay, that is your delta Hx value, that is hydrodynamic boundary layer thickness value, is 9.156. Right. What is the delta Tx now? For this, you need delta Hx. It is again 9 point.
4.78 into 10 to the power minus 3.
Yeah, let me do it. See here, you need a Prandtl value. Okay, this has to be obtained from the data book. So you refer to your data book. In your data book, the value is 7.0 020. So 7.020 to substitute. You also write this in the top right corner. The final value 0.7 point. What is that? 020. Yeah, tell me what is this? Thermal boundary layer thickness you are saying.
4.78 into 10 power
4.78 into 10 to the power minus 3.
4.782 into 10 to the power of minus 3 meters. Good. Now let us move to the delta x, that is a displacement thickness. It is delta hx by 3. It is 9.156 into 10 to the power of minus 3 by 3. Tell me what is this value?
2.052 into 10 power minus 3.
0.52 into 10 to the power of minus 3 meters. This one is by 7. By 7. Tell me what is this value?
1.3 into 10 power minus 3.
Meters. Okay. So here you got answers. These are the answers. What's happening? And these are also the answers. And apart from this, you have to calculate these things also. These are also asked in the question. 0.664 into the RE value, 2,98,201.73 or to the power of minus 0.5.
210.7.
The CFX value is saying
No, sir. Reynolds number you wrote 298,210.
210 is correct. Yeah, 210 is correct. Two one zero. Okay. So tell me what is the CFX value? Also calculate this 1.328 into 2,98,210.74 to the power of minus 0.5. Tell me these two values.
1.20 into 10 power minus
1.20 into, is that right?
3. Yes, sir.
CFL also you tell me.
2.43 into 10 power minus
10 power minus 3. Okay. So you are done with these things. Apart from this, okay, is also asking you what is the H value. You have to calculate what is the H value, and also using this H you have to calculate what is Q, that is HA into delta T. Also you have to calculate. So these are the things you need to get. So how to get these things? Okay, for getting these things you need NU formula. Okay, you have to choose an NU formula, appropriate NU formula from the data book. So go to the data book, refer to the page number 120 in the external flow case. See here, two cases we will remember very clearly. That is constant wall temperature case and constant heat flux case. Constant wall temperature case and constant heat flux case. So the constant wall temperature case formula is here. This one, NUX is equal to this whole thing. I will write this here. So the Nu is equal to 0.332 into Rex whole to the power 0.5 into Prandtl to the power 0.33. Okay, so that is your Nu expression. So now you have everything on the right hand side. On the right hand side, you know what is the Reynolds number formula. Sorry, Reynolds number value, you know it. And the Prandtl number value, it is 7.020. You know everything on the right hand side. So you will get what is the Nusselt number value. Tell me what is the Nusselt number value.
346.92.
346.92 is your Nusselt number value. So basically what you need is H. So you have to express Nu in terms of HL by K here. See, this Nu is actually NUX. If you carefully look at this formula, it is NUX. Okay, NUX means what? You have to put that appropriate X here. Is equal to L. So I put Nu is equal to HL by K. Okay, so that's what the subscript meaning is. It is X means HX by K, but X is equal to L here. Okay, let me write that Hx by K also here. Since X is equal to L, we will be doing it like this. So 346.92. So that will imply H into L value. What is the L value here? It is 1.
1.
The K value, you need it from the data book. So go to your data.
0.597.
What is that?
597.
0.5978 from the data book. You will get it as 0.5978. So what is the H value?
207.3.
207.3 watt per meter square Kelvin. Okay, this is your H value. This is he's asking in the question. Okay, so you're done with H. Apart from this H, he's also asking you to calculate what is called as Q. So to calculate the Q is equal to H into A into the delta T. What is the delta T here?
20.
10.
The delta T means T wall minus T infinity. See, always the delta T in HA delta T should be the difference of solid and fluid temperature. Solid and fluid temperature. Always it should be solid and fluid temperature difference in HA delta T. So it is wall minus flow, that is T infinity. So here the value of T wall is what?
10.
What is it given in question? It is given as 10 degrees centigrade. What is the fluid temperature?
30.
30. So you will substitute those values here. Okay, so that is the thing. And then what is the thing with A? What is area here?
1.
Area is area with which the fluid is interacting. Here, if you have a plate here like this is a plate, and thickness direction I am showing you here, but fluid is flowing over this like this. It is coming here and flowing over like this. It's coming here and flowing over like this. Okay. So if I have to show you the area here, the area is on the top. Let me draw it clearly. Okay, it's like this, and this is 1 meter, and this is also 1 meter. So if you want area here, the area is this one, the top area. Okay, this whole area should be taken. So this area is area with which the fluid is interacting. So this will be, in this case, it is 1 into 1 meter. Okay, 1 meter by 1 meter. That's what is given. So everything you know, H is also known to you. It is 207.3. Simply substitute all of them, you'll get Q value. So the Q is 207.3 into 1 into 1 into 10 minus 30. Tell me what is the value?
4148.6.
4 1. Yeah, 4 1 is not a right answer. Actually, you have done it correct. Okay, I must tell you one thing here that I missed here. That's why your answer is wrong. See here, see when you write this NUX here, very important thing you must understand is this NUX is an average. This NUX is an average value. Average. This is average value. No, no, this is a local value actually. I must say that this is local value. So what you find out of this will be a local heat transfer coefficient. Where is it written? See here. NU, if you are writing simply, it is up to location L. Okay. If it is written NU bar, if it is written NU bar, it will represent the average. So it will be representing the average. If you want to go for the average value here, what I have to do is NU bar is 2 times NUL. This formula you have to take care into the calculation. So while calculating the H, this H that you have calculated here is a local H. But if you need the H value average, H average will be equal to 2 times the H local. Okay, how do we get this? This is from page number 122, 1.3. From this concept, you will get this formula. Okay, because NU bar is equal to 2 times NU. Remaining things will get cancelled. That is H by K on left hand side and H by K on the right hand side will get cancelled, and you will get this formula. So this will be like 2 into 207.3 you have to take. So it will be like, what is 414.6. So watt per meter square Kelvin. So here you should not submit this 207. This is wrong. What you have to submit? You have to submit. You have to substitute 414.6. Here 414.6. So that is correct. Okay, into 2 times you do your answer and tell me.
8292.
8292. watts is your Q value. Is it clear? Do you have any questions at this level?
Sir, why we should not take the area at bottom also?
Why we should not take the
Area at the
area,
bottom
the,
two times.
yeah. See
What,
here,
sir?
you are saying this similar area will be available at the bottom also. Okay. So you can take that area also into this, not a problem. But that will represent the area on both sides. You got it?
Yes, sir.
So it will represent the heat transfer on both sides. If you are doing it for one area, it will represent heat transfer only on one side. Okay. So in question, what is asked the refrigeration, isn't it? Let me go to the question. He has given that the refrigeration required to maintain the plate temperature, he's saying. So the plate temperature is overall maintained at 10 degrees centigrade. So one side you have done, the other side also you can take and do. It's up to you as per your requirement. Because it is not clear in the question, I've done it only on one side. Is that okay?
Yes, sir.
Right. So let's begin. Yeah, we have to solve the next problem here. I have updated these things in your Google Doc. You can refer to. And, right. Here we have one more problem. In this problem, we have a different kind of material here. Sodium potassium alloy, 25 and 75%. Sodium, that is Na, and potassium, that is represented with K. It is 25% and 75% uh, is the value given. The percentage values are given for this alloy composition. That is the material given to you, and it's written that it is flows over. Flows over means it is external flow. External flow over what? Over a plate. Over a flat plate. Over flat plate. This is the case, and is given 300 degrees centigrade to you. This 300 degrees centigrade is T infinity. That is temperature of the fluid is 300 degrees centigrade, and it is given as 20 centimeters. You can call it as L. Okay, because in this direction the fluid is flowing, so you will call that as L. And then the plate temperature is 500 degrees centigrade. Long plate element is at 500 degrees centigrade. So T wall is 500 degrees centigrade. Then what is given in question is also given you a velocity, free stream velocity of 0.6 meters per second. The velocity is equal to 0.6 meters per second, and the width of the element is also given. Width is given as 0.1 meter. Determine the hydrodynamic and thermal boundary layer thickness, and also the displacement thickness and momentum thickness. So what he's asking you to find delta Hx, delta Tx, delta x, delta ix. What are all these values? He's asking. And determine also the local and average value of coefficient of friction, that is CF X and CFL bar. These values he's asking you to find, and the convection coefficient is asking also find the heat transfer rate. H value he's asking, Q value is asking. More or less, this is the same kind of question that we have solved till now. But the only difference in this one is the material has changed significantly. So we have to cross refer to the material values very carefully. So where is this material in our data book? Can somebody tell me where is this material? See, keep moving in your liquids page itself. In liquids page, you will have water, ammonia, carbon dioxide, glycerin, sulfur dioxide, something, 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 something like that. Keep going. Here, here you can find the values of alloy. That alloy of sodium Na and potassium K. So all the values are given to you here. So what do you have to do? First thing, once you know the kind of flow here, you have to find out something called as film temperature. The film temperature is an average of T wall plus T infinity. So this is what it is. The T wall is 300. T infinity is 300. T wall is 500 plus 300 by 2. What is it? 400 degrees centigrade. TF is 400 degrees centigrade. What you have to do? So you have to get the properties at 400 degrees centigrade. Okay. So you have to get the properties at 400 degrees centigrade. Same kind of thing that we have done in the previous problem. So get the value of RE. What is the value of RE formula here? V into X by mu. Okay, you know V value given in question. The V value given in question is 0.6, and L value given in question is 20 centimeters. So 20 into 10 to the power of minus 2 by new value you have to get from the data book at 200 degrees centigrade. 200 or 300? What is that?
400.
400. 400. That's 400 to get the new value. It is 0.308 10 to the power of minus 6. It's measured in meter square per second. Yeah. 308 into 10 to the power of minus 6 meter square per second. That's the new value, 0.308 into 10 to the power of minus 6. Quickly tell me what is the value of this one, REX?
38961.03.
38961.03. Am I right?
10 point.
10.3 or
Yes, sir.
0.3. So this is like 3,89,000. So RE value is less than 5 lakhs. So RE is less than 5 lakhs. So that will imply it is a laminar flow. Okay. So that's it. The remaining part, you solve it for yourself using the properties that are there in page number 41. Okay, so the remaining part is more or less the similar kind of thing. So I would not like to repeat it again here because the problem is the same thing. So you do it for yourself. Okay. So do it yourself. Maybe if you have any questions, let's discuss them in the next class. And now let me move to the next problem. That is the engine oil one. In this question, the material is given as engine oil and it is flows over a flat surface. So it's an external flow over flat plate. This is engine oil, and engine oil value is given. It is T infinity, it is 80 degrees centigrade. T wall is given as 40 degrees centigrade. The velocity is given as 2 meters per second, and determine the distance of 0.4 meter from the leading edge, the hydrodynamic and boundary layer thickness. So what he's giving you is he's giving you x essentially here, and this x is 0.4 meter. See, we are not taking this as L because from the leading edge he is giving you certain distance, and the overall distance he has not given to you. So you don't know whether the flow is over the 0.4 meter or not, but that is not required for you here. Since it's giving that distance of 0.4 meters from the leading edge, you will use it as x and solve the thing. Okay. Also determine the local and average values of friction coefficient and convection coefficient. Right. So what you have to do here, you have to get hydrodynamic boundary layer thickness delta Hx, delta Tx, and you also have to get the CFx and CFL. CFL means average. Okay, all these things he's asking. Along with this convection coefficient also he's saying. So H, what is the H and what is H bar? He's asking. So this is your question. So again, it's a kind of similar question as far as these four are concerned. It is similar. Okay, but the remaining two it might be different. So for that, what you have to do, first you have to get the value of TF. The TF is T wall plus T infinity by 2, that is 80 plus 40 by 2. What is this value? It should be 60 degrees centigrade. So you have this TF at 60 degrees centigrade. So properties are to be evaluated at 60 degrees centigrade from the data book. You'll get so and so page number. You'll leave some space at the top right corner for writing the properties. So let's move to the calculation of Reynolds number for getting whether the flow is laminar or turbulent. So for that, what you have to do, you have to get it like V into X by mu. So the V value is given in question as 2 and the X value is given as 0.4. New value is unknown to you, and new value you have to get from the data book. This value has to be obtained from the data book. Can somebody tell me what is the page number for engine oil in the data book?
33.
Thank you. Page number 33. Page number 33. Thank you. Here you can see there is an engine oil. This is also sometimes called as lubricating oil. For 60, the values are given directly here. You can use it. 83 into 10 to the power of minus 6 meter square per second is the kinematic viscosity. 83 into 10 to the power of minus 6. Substitute that value here. You will get the Reynolds number value. Tell me what is the Reynolds number value. Fast. What is the Reynolds number value?
Nine six three 8.55.
9655.
38.55.
That is the Reynolds number value. So the Reynolds number value is less than 5 lakhs. That implies the flow is laminar. Flow is laminar. So once you know that the flow is laminar, you can use all the formulas that are there for delta Hx, delta Tx, delta Ix, delta Ex, and delta Ix, and Cfx and Cfl bar. All these formulas, as it is, you can use from the data book and solve for. Okay. But when it comes to H, what you have to do is a different story. So these things solve for yourself. But when it comes to H, let us discuss here now. See, H, what you can do in general, you will go to this page and you will see that it is a constant wall temperature case, and you will use this formula and solve it. That is the one way of solving the given case. But here you may not use this particular formula here. What you have to do is you have to use this one. See here is written for high Prandtl number values, that is silicons. You have to use this formula. Okay. The Prandtl numbers greater than 50, you have to use this. So if you go to data book and look at the Prandtl number values for this engine oil, you look at this. All these values are very high. So whenever engine oil is given to you, you have to be careful. Okay, you have to take this seriously because the Prandtl number value is greater than 50. Since the Prandtl number value is greater than 50, you have to use this formula here. Okay, so use this formula and solve it. So let me write that formula here for you. The Nu is equal to 0.3387 into Rex power 0.5 and Prandtl power 0.333 by 1 plus 0.0468 by Prandtl whole to the power 0.67 whole to the power 0.25. This is how it should be written. This should be something like this. There seems to be a mistake. So kindly correct it. A simple thing, you will understand that. Okay, that's how Nusselt number should be calculated. And then you will get the H value here. So this is for the high Reynolds number case. See, in the previous problem that we have seen, even for that also, you can use this particular formula, this formula. Okay, why this formula can be used there? Let me move to the problem. See, in the problem, what is given is given as sodium potassium alloy. What is sodium potassium alloy? This sodium potassium alloy is actually a liquid metal. See, when you go to this one here, in the previous problem, this alloy is nothing but a liquid metal. So For liquid metal, what is the formula given here on the top here? You can see the low Prandtl number values. The Prandtl number value is less than 0.05. Here you can see the Prandtl number values less than 0.05. The Prandtl number values are less than 0.05. So you can use this formula even for the previous case. Okay, for problem, for previous problem also. Okay, so I covered these two in bit hurry with an intention that you will solve it for yourself. So keep that in mind.